If you are an engineer, mapping out a new factory floor today, your biggest enemy isn't really the budget
Yeah.
or the supply chain or even the real estate. It's the 500-gallon vat of highly combustible fluids sitting directly in the middle of your, otherwise perfectly optimized layout.
Oh, absolutely. It changes everything.
Yeah. Usually when we talk about industrial engineering, there is this expectation of total control. You place the assembly line here, the packaging station over there, and you manage the flow of solid materials and human capital with a kind of clean, rational predictability.
Mm-hmm.
But the moment you step into the world of industrial dipping, coating, and printing operations, that illusion of total control completely vanishes. You aren't just managing solids and timelines anymore. You are managing massive open pools of fuel.
That shift in state, from solid components to volatile liquids, it completely rewrites the calculus of facility design.
How so?
Well, because when things go wrong with thousands of gallons of exposed flammable liquid, you aren't looking at a minor bottleneck on an assembly line. The physical characteristics of the hazard mean a localized failure can escalate exponentially.
Like almost instantly, right?
Exactly. We are talking about rapid fire progression, intense thermal radiation, and the generation of explosive vapor clouds. The margin for error basically drops to zero.
Which is the entire reason we are unpacking this today.
Okay.
Okay, let's unpack this. If you are an industrial engineer tasked with designing a factory layout from the ground up, or maybe a facility manager upgrading safety protocols, or just an insanely curious mind who wants to know the mechanics of keeping a manufacturing plant from turning into a crater, this is for you.
Mm-hmm. Mm-hmm.
We are pulling the primary fire protection goals hidden inside NFPA 34, the 2021 edition. That is the standard for dipping, coating, and printing processes using flammable or combustible liquids.
It's a dense read, but so important.
It really is. And reading through this source material, it becomes obvious very quickly that this isn't just like a list of bureaucratic demands. It is a highly sophisticated engineering manual written in the ashes of past industrial disasters.
Yeah, that's a good way to put it.
Every single rule, from a required overflow drain to a highly specific ventilation calculation, is designed to interrupt the physics of a catastrophic fire.
Yeah, the standard really forces you to understand the fundamental mechanics behind the hazard. You have to anticipate fluid dynamics, thermal mass, and even human behavioral psychology during a panic.
Wow, human psychology too.
Oh, definitely. The code is structured to build these concentric rings of defense. And the very first ring of defense actually has nothing to do with the machines or the chemicals themselves.
Okay, what is it?
It's the geography of the room they inhabit, location and structural isolation. Before we look at the machines, we have to look at the room.
Let's start right there. We have to build this layout from the ground up, and the first decision is where to put the room. According to the standard, dipping, coating, and printing processes inherently belong in what they call industrial occupancies. That's like their natural habitat.
Right.
In a dedicated industrial occupancy, the baseline requirement is that the area must be protected with an approved automatic sprinkler system designed to NFPA 13 standards.
Which makes sense. But real-world manufacturing is messy.
Yeah, exactly. A business might need to integrate a massive coating process into a mixed-use building. Maybe there's a mercantile area attached, or, I don't know, an educational facility on the same campus.
And the moment you introduce a high-hazard fluid process into an occupancy that isn't strictly industrial, the architectural requirements become incredibly severe.
I'd imagine. You can't just put up some drywall.
No, you definitely cannot just drop a spray booth into the corner of a mixed-use warehouse. The code demands a minimum 2-hour fire resistance rated separation.
Right, the horizontal and vertical separation.
Exactly. And this isn't just a thick drywall partition. A 2-hour rating means the physical barriers, so the walls, the floor, the ceiling, must be constructed and tested to withstand an intense direct fire exposure for 120 minutes without structurally failing, or, allowing the passage of flame and extreme heat to the other side.
I was actually looking at the testing parameters for those fire-rated assemblies, and it is brutal. They follow the ASTM E119 standard time temperature curve.
Oh, yeah. That test is no joke.
Within the first 5 minutes of the test, the ambient temperature in the test furnace hits 1,000 degrees Fahrenheit.
Yep.
And by the end of the 2 hours, it is pushing 1,850 degrees. At that temperature, standard building materials don't just burn, they literally disintegrate. I mean, steel beams lose their structural integrity and turn to noodles unless they are heavily insulated.
Which is exactly why achieving that true 2-hour separation requires specialized construction. You're looking at reinforced concrete, masonry, or thick layers of specialized fire-resistant gypsum over heavily protected structural members.
You are essentially building a fortified vault inside your building.
Precisely. The logic is containment. If the active suppression systems fail, that 2-hour window gives the fire department time to arrive, set up, and aggressively attack the fire before the structural integrity of the entire shared building is compromised.
And there is one location rule that the standard is completely uncompromising on.
A basement ban.
Oh, yes. The basement ban.
NFPA 34 states that processes using flammable or combustible liquids should not be located in basements.
Right.
I know a lot of facility planners fighting for square footage in urban environments might look at a massive, empty subterranean floor and think it's the perfect place to hide a giant dip tank.
They try it all the time.
So let's assume I'm that engineer, right?
Yeah.
I've got a tight floor plan. I want to put the tank in the basement, but I swear, to pack the ceiling with high-density sprinklers, double the water supply, and just completely over-engineer the active suppression. Why won't the code let me do that? Well, relying purely on overhead sprinklers completely ignores the behavior of the specific chemicals you're using. Sprinklers are designed to control heat and knock down flames,
Okay.
but they do absolutely nothing to mitigate unignited pooling solvent vapors.
Ah, the vapors.
Yes. The physics of flammable solvents dictate this rule. The vapors evaporating off these liquids are almost entirely heavier than air. They don't dissipate upward into the atmosphere like smoke from a wood fire.
So they just sink.
They behave much more like an invisible fluid. They flow over the lip of a tank, cascade down stairwells, and seek the lowest possible point. So in a basement, those vapors accumulate right at the foundational bedrock of your facility.
Wait, so even if the room is cold and nothing is actually burning yet, the basement is slowly filling up with a highly explosive gas mixture.
Precisely. You have a massive explosion risk just waiting for a single spark from a forklift or a dropped wrench.
That's terrifying.
And if an ignition occurs in a subterranean level, the resulting overpressure event doesn't just blow out windows like it might on a top floor. The explosive force is trapped by the foundation walls and the floor above it.
So it pushes against the structure itself.
Right. An explosion down there can sever the primary load-bearing columns of the structure. You could literally drop the entire multi-story facility into its own footprint.
Oh, wow. So the whole building comes down.
Exactly. Add to that the human element of egress. A flash fire in a basement forces personnel to travel up and out, fighting against gravity, while toxic smoke and extreme heat are expanding in the exact same upward direction. You're basically trapping workers in a chimney.
And let's not forget the water problem. Let's say a fire breaks out. Your massive basement sprinkler array activates, and it successfully suppresses the fire. Where do thousands of gallons of water go?
Nowhere.
Right. A basement has nowhere to drain naturally. You end up flooding the lower level. And because most flammable solvents have a lower specific gravity than water, the burning solvent simply floats on top of the rising floodwaters.
It's a nightmare for firefighters.
You create a rising tide of fire that spreads across the entire basement floor plan.
It's true. Now, the standard does provide an incredibly narrow window of exceptions to this basement ban, but the engineering hurdles are monumental.
Like what?
If you absolutely must use a basement, you are required to meet strict means of egress requirements from Chapter 40 of NFPA 101, guaranteeing multiple clear paths out. You also have to construct dedicated access routes for emergency responders so firefighters aren't walking blindly into an underground oven.
That makes sense.
And most importantly, you have to design and install an active mechanical vapor capture system that physically pulls those heavy combustible gases off the floor and exhausts them safely outside the building envelope.
Wow. Okay, speaking of the building envelope, we have to talk about the materials lining this room. The code dictates the use of non-combustible or limited combustible materials for the process area, and it defines limited combustible with a very specific metric. It refers to materials that have a peak heat release rate not exceeding 150 kilowatts per square meter for 10 seconds.
That metric is really the cornerstone of passive fire protection. Heat release rate is arguably the single most important variable in a fire's growth.
More than just what the material is made of.
Oh, absolutely. It doesn't just measure whether a material will burn, it measures how fast and how violently it releases its stored energy when exposed to heat.
I guess it's kind of the difference between a thick oak log and a pile of dry pine needles. They might have the same total mass, but the pine needles release their heat almost instantly, causing a massive spike in temperature.
That is the core issue, yeah. When material scientists test this, they use a device called a cone calorimeter.
A cone calorimeter.
Yeah. They subject a sample of the building material to an intense radiant heat source and measure the oxygen consumption as it combusts. If a material releases more than 150 kilowatts of energy per square meter, it contributes so much thermal energy to the room that it accelerates the fire toward flashover.
Flashover being the point where every combustible surface in the room ignites simultaneously, right?
Exactly. By capping the wall and ceiling materials at that 150 kilowatt limit, the standard ensures that the structure itself won't feed the fire. You are starving the fire of secondary fuel sources.
Okay, so we've engineered our room.
Yeah.
It's above grade, it's structurally separated, and it won't contribute its own energy to a fire. Now we move to the physical design of the equipment.
The microenvironment.
Right. The vats, rolls, and conveyor systems holding the hazardous liquids. We are designing the danger zone itself.
And the foundation of this microenvironment is the construction of the dipping and coating tanks themselves. The standard mandates rigid, securely supported tanks made of non-combustible materials like steel, concrete, or solid masonry.
Right.
But the critical engineering challenge arises with scale. If a tank exceeds 1,900 liters, which is roughly 500 gallons, or if it has more than 1 square meter, which is about 10 square feet, of exposed liquid surface area, its supports need a 1-hour fire resistance rating.
That specific 500-gallon threshold is fascinating to me. It recognizes the tipping point of thermal mass.
Exactly.
Like if a fire starts in a small 50-gallon vat, the room might get hot, but the structural legs of the vat probably won't fail before the sprinklers knock the fire down.
Right.
But 500 gallons of burning solvent generates an immense, sustained heat flux. If the steel legs of that massive tank aren't insulated or fire-rated, the heat will quickly bring the steel up to its critical failure temperature around 1,000 degrees Fahrenheit, where it loses about 50% of its yield strength.
And if those steel supports buckle, the tank collapses. You instantly dump 500 gallons of burning fuel across the factory floor.
Which is a disaster.
Total disaster. You have taken a localized, contained tank fire and turned it into a massive, uncontrolled, three-dimensional spill fire. You have to keep the vessel standing upright, even when it's engulfed in flames, long enough for the active suppression systems to perform their function.
Keeping the fluid inside the tank leads perfectly into my absolute favorite hyper-specific engineering rule in this entire code.
I think I know which one you're talking about.
It's found in section 5.5, the 6-inch rule.
Yes.
The liquid level in any dipping or coating tank must be maintained at least 150 millimeters, which is 6 inches below the top of the tank. Furthermore, the top of the tank itself must sit at least 6 inches above the floor level.
It seems almost too simple, right? An arbitrary 6 inches of empty space. But the fluid dynamics and the suppression mechanics behind that rule are brilliant.
I was trying to visualize the physics of this. It's like if you were carrying a full cup of scalding hot coffee while running to catch a train, and you have filled that mug to the absolute brim, the slightest disruption causes a disastrous spill.
Right.
A stumble, a gust of wind, just the kinetic movement of your arm. You need that lip of empty space to absorb the sloshing.
That's a perfect analogy. Now, apply that physical reality to an industrial fire. When a fire breaks out on the surface of a 500-gallon dip tank, your automatic fire protection system activates. Whether it is a high-pressure water mist system, a dry chemical extinguisher, or a high-expansion foam system, that suppression agent is discharged from overhead nozzles directly downward onto the liquid surface.
Right, it's spraying down hard.
The agent exits those nozzles at high velocity. It carries significant kinetic energy.
It's essentially bombarding the surface of the fluid.
Exactly. It creates violent turbulence and downward displacement. If the flammable solvent is filled to the very top edge of the steel tank, the sheer physical force of the fire suppression agent slamming into the liquid will physically push the burning fuel over the edge.
Oh, wow. So the system putting out the fire actually causes a spill.
Right. The very system designed to extinguish the fire ends up splashing burning solvent onto the surrounding floor. That 6-inch freeboard acts as a kinetic buffer zone.
It gives the agent room to work.
Yes, it gives the extinguishing agents the physical displacement volume they need to violently impact the surface, agitate the liquid, and smother the fire without overtopping the tank walls.
But the code doesn't just stop at the top of the tank, it dictates the bottom as well. Tanks exceeding 570 liters, or about 150 gallons, are required to have bottom drains capable of emptying the entire liquid contents in under 5 minutes.
Yes, the bottom drains.
And that liquid can't just dump into a floor trench, right? It must drain into a dedicated closed salvage tank that is physically larger than the main tank itself.
This is a requirement that layout engineers and financial planners frequently agonize over.
Because of the cost.
Cost and space. It consumes valuable underground or adjacent square footage. You have to excavate, design, and install a massive, highly fortified empty tank whose sole purpose in the facility is to sit there, entirely unused, waiting for a worst-case scenario.
Right. Let's extrapolate the consequences of ignoring this. Say an engineer decides to value engineer the salvage tank out of the project to save some money. They just bolt a 1,000-gallon dip tank to the floor without a bottom drain. What is the actual mechanic of failure when a fire starts?
Well, without a bottom drain in a salvage tank, you are forcing your active fire suppression system into a brutal war of attrition.
A war of attrition.
Yes. A fire ignites in that 1,000-gallon dip tank. The overhead sprinklers or the foam nozzles deploy and begin beating back the flames. But the entire thermal mass, the total fire load of those 1,000 gallons of fuel, remains sitting directly inside the active workspace.
So it just keeps fueling the fire.
Exactly. It becomes a prolonged high-intensity burn. You are relying completely on your suppression system, having enough sustained water pressure or chemical agent to permanently cool and smother a massive pool of boiling solvent.
And if it runs out?
If the municipal water pressure fluctuates, or if the foam tank runs dry after 10 minutes, the fire simply reignites from the residual heat in the tank walls and continues to burn until it overwhelms the room's structural integrity.
Wow, so the bottom drain completely changes the battlefield. The moment a fire is detected, a heavy-duty valve at the bottom of the tank opens. Over the next 5 minutes, gravity simply pulls that 1,000 gallons of fuel out of the burning room and safely routes it into an underground, oxygen-starved salvage bunker.
You are physically removing the fuel source from the fire triangle.
The flames on the surface of the dip tank literally starve and die because the liquid fuel runs down the drain. It is an incredibly elegant, gravity-fed solution to a complex thermodynamic problem.
It really is, and we must also account for the reality of water displacement.
Oh, right, because of the sprinklers.
Yes. If standard water sprinklers are discharging over an open tank, the water will eventually accumulate. Because water is heavier than most industrial solvents, the water sinks to the bottom of the tank and the burning solvent floats upward.
Oh, I see. So it pushes the burning liquid up.
Right. Without mitigation, the water will eventually float the burning solvent right over the top edge of the tank. To prevent this, the code requires overflow pipes positioned strategically below the top lip, drain boards that heavily slope away from the tank back to a safe catchment, or heavy automatic closing covers triggered by fusible links.
Which naturally leads to the systems dragging materials through these tanks, the conveyors.
Yes, the conveyors are critical.
The code demands that continuous conveyor systems must be interlocked to stop automatically in the event of a fire, or if the facility's mechanical ventilation system fails. I mean, you absolutely cannot have a conveyor belt continuing to drag freshly coated, highly flammable, burning products out of a dip tank and parading them across the factory floor.
No, definitely not. You are trying to isolate the hazard. If the conveyor keeps moving, it acts as a mechanical vector, spreading the fire to the drying ovens, the packaging area, and the rest of the facility.
But while reviewing the code, I found a brilliant exception to this rule: web or sheet transport systems in printing processes.
Yes.
Imagine massive, continuous rolls of paper or plastic film feeding through a high-speed industrial printing press. They are explicitly not required to stop if stopping them would create a more hazardous condition.
This is a perfect example of the code deferring to nuanced operational realities rather than rigid checklists.
How does that work in practice?
Well, in high-speed web printing, that continuous substrate, the paper or plastic, is moving at incredible speeds through high-heat, gas-fired drying ovens to flash off the ink solvents.
Right.
If a minor fire starts in a different section of the press and the interlock immediately kills the main drive motors, that continuous web of paper stops dead in its tracks.
And a large portion of that paper is now sitting perfectly still inside a 400-degree oven.
Exactly. The ambient heat inside the oven will bake the stationary paper until it reaches its auto-ignition temperature. By hitting the emergency stop, the interlock has inadvertently created a massive secondary fire deep inside the confined space of the drying ovens, which is far harder to extinguish.
Oh, wow. So stopping it makes it worse.
Much worse. So the code grants engineers the authority to make a critical judgment call. If letting the drive motors run to pull the web out of the oven safely prevents a catastrophic secondary ignition, you are allowed to keep the motors spinning during the initial fire alarm sequence.
Okay, we've now engineered a fire-rated room. We have our steel tanks with the 6-inch kinetic buffer, and we have our 5-minute gravity drains. The liquid fuel is contained.
But containing the liquid is only half the battle.
Right, because the liquid cool itself isn't what catches fire first. It's the invisible vapor evaporating off the surface of that liquid.
Yes.
And you can't put a 6-inch steel lip on an invisible gas. Controlling that gas requires manipulating the air pressure itself. This is the domain of mechanical ventilation and electrical area classification.
Here is where structural layout design merges with fluid dynamics. You are managing an invisible floating threat. The code mandates that mechanical ventilation systems must confine flammable vapors to no more than 1,525 millimeters, exactly 5 feet from the vapor source.
5 feet.
Yes. That means the active exhaust hoods must be engineered to pull air so aggressively that if you were to test the atmosphere 6 feet away from the edge of the dip tank, you would register zero trace of solvent vapor.
It creates a strict aerodynamic boundary layer.
Exactly.
But there's a mathematical limit to what can safely exist inside those exhaust ducts. The code enforces the 25% LFL rule. The concentration of vapor in the exhaust air streams must never exceed 25% of the lower flammable limit, or LFL, of that specific vapor.
To understand the importance of that rule, we really have to define the lower flammable limit.
Let's do it.
The LFL is the absolute minimum concentration of a specific combustible vapor in the air that is capable of propagating a flame if exposed to an ignition source. If a solvent vapor has an LFL of 2% and the air in your room contains only 1% vapor, it physically cannot burn. The fuel-to-air mixture is too lean.
Too lean. Got it. But the solvents used in heavy industrial coatings have terrifyingly low LFLs. I mean, a 1% or 2% vapor-to-air ratio is often enough to create an explosive atmosphere. So why does the code restrict the exhaust duct concentration to only 25% of that limit? Why not push it to 80% or 90% for maximum efficiency?
Because operating at 80% leaves absolutely no room for the unpredictability of fluid dynamics. By capping it at 25%, the standard builds in an aggressive, mandatory 4-to-1 safety factor.
Why do we need that big of a margin?
Well, in an active industrial setting, conditions fluctuate wildly. A worker opens a massive roll-up bay door, changing the room's atmospheric pressure. The ambient temperature spikes on a hot summer day, accelerating the liquid's evaporation rate. Or there's a sudden temporary surge in the production line speed.
Any of those events can cause a sudden, localized spike in vapor generation.
Exactly.
And because these vapors are heavier than air, they don't disperse evenly like, a drop of food coloring in water. I imagine it more like pouring thick, heavy syrup into a glass of water without stirring it. The syrup sinks and pools at the bottom, creating highly concentrated zones.
That is the perfect mechanism to visualize. Vapors slug. They travel in dense, concentrated pockets.
Slugs of vapor.
Right. If your exhaust fan suddenly sucks up one of these concentrated slugs of heavy vapor, the concentration inside the ductwork will violently spike. If you are already operating at 90% of the LFL, sucking up that slug pushes the interior of your metal ductwork past 100%.
Oh my. The inside of your exhaust pipe just became a bomb waiting for a static spark.
Precisely. But with the 25% limit, you have the mathematical headroom to absorb that sudden influx. The 4-to-1 safety margin ensures that even if a dense slug enters the system, it gets diluted by the high-volume airflow before it ever reaches an explosive concentration.
That is so smart. But wait, that raises a terrifying vulnerability.
What's that?
My entire facility's safety is completely reliant on these massive exhaust fans spinning constantly, just pulling all this flammable, invisible vapor out of my 500-gallon dip tank. What happens if a fan belt snaps? What if a motor burns out or the facility loses power? Does the room just silently fill with heavy gas and wait for a spark?
That specific scenario is the nightmare that drives safety engineering. And it is exactly why the code mandates unyielding electrical interlocks.
Unyielding.
Yes. If the mechanical ventilation system fails, if the airflow sensors detect a drop below a required pressure, or if the fan loses power, the entire dipping and coating process must automatically and instantaneously shut down. And a high decibel alarm must sound. Instantly. The apparatus physically cannot function without the exhaust fans running. The power supply to the fluid pumps, the conveyor drives, the coating applicators, they are all electrically slaved to the pneumatic sensors inside the exhaust duct. If the air stops moving, the power to the process is instantly severed.
It's a dead man's switch for the entire factory floor.
Exactly.
And you can't just suck thousands of cubic feet of air out of a room without replacing it, right?
No, you definitely cannot.
The code demands engineered makeup air to balance the room pressure. If you don't supply dedicated clean air, your massive exhaust fans will pull a vacuum on the room, fighting against themselves, straining the motors, and ultimately failing to remove the vapors.
Right. It's a closed system, essentially.
Furthermore, those exhaust ducts have to take the shortest, most direct route outside the building envelope. You are forbidden from routing highly flammable exhaust piping through, like the drop ceiling of the employee break room.
That would be a very bad idea. And this movement of invisible vapor dictates the electrical area classification. This defines where you are legally allowed to place anything that uses electricity.
Okay, break that down for us.
The code breaks the space down into hazardous zones. You have Class I, Division 1 and 2, or the Zone 0, 1, and 2 systems. This answers the fundamental layout question. Where can I safely mount a lighting fixture, a motor, or an electrical subpanel?
Let's look at the engineering behind those classifications. In a Division 1 or Zone 0 environment, which is directly at the surface of the liquid or inside the enclosed vapor tunnel, ignitable concentrations of flammable vapors are expected to be present continuously under normal operations.
Yes, it's the most hazardous area.
You absolutely cannot install standard electrical equipment there. Anything electrical must be either intrinsically safe or explosion-proof. But those two terms aren't interchangeable, are they? The engineering approaches are completely opposite.
They're entirely different philosophies of protection, yes. An intrinsically safe device approaches the problem by limiting energy.
Limiting energy, how?
Well, every combustible gas requires a specific minimum amount of thermal or electrical energy measured in millijoules to ignite. Intrinsically safe wiring uses components like Zener diode barriers to heavily restrict the voltage and current.
Oh, okay.
It throttles the electrical energy so severely that even if a wire breaks and snaps a spark, that spark physically lacks the thermal energy required to ignite the surrounding vapor cloud. It operates below the ignition curve.
So intrinsic safety prevents the spark from ever getting hot enough. What about explosion-proof?
Explosion-proof equipment concedes that a spark will happen and the vapor will ignite.
Wait, really? It lets it ignite?
Yes. An explosion-proof motor, or light fixture, is built with a massive, heavy-duty cast metal enclosure. When vapor seeps into the housing and an internal spark ignites it, a small explosion occurs inside the casing.
But the casing doesn't blow up.
Right. The casing is engineered to physically withstand the extreme overpressure of that blast without rupturing. More importantly, the joints and flanges of the casing are precision machined to create a flame path.
A flame bath.
Yeah. As the superheated, expanding gases from the internal explosion try to escape through the tiny gaps in the metal flanges, the heavy metal absorbs the heat. By the time the escaping gas reaches the outside atmosphere of the factory floor, it has been cooled below the ignition temperature of the room's vapor cloud.
That is an incredible piece of engineering. You are literally quenching a flame by forcing it through precision-milled metal mazes.
It really is brilliant.
And the electrical concerns aren't just limited to plugged-in devices, are they? The standard devotes significant attention to static electricity.
Oh, static is a huge issue.
The friction of liquids flowing rapidly out of a pipe, or a plastic web rolling rapidly over a metal drum, generates a triboelectric charge. That static charge can easily build up thousands of volts, snapping a spark that packs more than enough millijoules to ignite a 1% vapor cloud.
Which is why every single conductive object in the process area must be heavily grounded and bonded to safely dissipate static buildup into the earth.
Though we must highlight a specific operational exception here for massive printing processes like flexography, gravure, and lithography.
Right, the printing exception.
Because these printing presses are inherently massive open-air operations with long webs of paper flying through the room at high speeds, they cannot be boxed into tight, mechanically exhausted enclosures like a small dip tank.
No, they're too big.
Therefore, the strict electrical classification rules for enclosed processes do not apply to them in the same rigid way. Engineers have to map and classify the open space around the individual ink fountains and the drying rolls, which requires a much wider, custom-calculated application of the zone mapping based on specific airflow patterns.
It's much more complex for those open processes.
So we have designed a mathematically safe architectural vault. We have built robust steel tanks with 6-inch kinetic buffers and rapid bottom drains. We have controlled the invisible vapor clouds with interlocked ventilation and intrinsically safe wiring.
We've done a lot.
But human history dictates that despite every passive safeguard, fires still happen. And when ignition occurs, your active fire protection systems and interlocks must execute a flawless automated cascade of events in a fraction of a second. This is the ultimate backstop.
This is the moment layout design transcends passive architecture and becomes a highly reactive thinking machine. The code dictates the doctrine of simultaneous discharge.
Simultaneous discharge, meaning everything at once.
Yes. If a thermal sensor or a flame detector registers a fire, your extinguishing systems, whether relying on high-pressure water mist, carbon dioxide, dry chemical powder, or a clean agent, must be engineered to discharge into the entire protected area simultaneously. It must be a total, overwhelming assault on the environment.
You can't just aim a sprinkler at the center of the dip tank.
No.
You have to simultaneously blast to the tank surface, the sloped drain board where fluid drips, the freshly coated workpieces hanging on the overhead conveyor, and the interior volume of the exhaust ducts.
Because if you successfully extinguish the dip tank but leave a single flaming part hanging on a conveyor hook 3 feet away, the radiant heat or dripping ember will simply reignite the tank a minute later.
Okay, here's where it gets really interesting. While that physical suppression agent is violently deploying, the facility's electronic brain is executing what Section 9.4 calls the interlock cascade.
Yes, Section 9.4.
I look at the Section 9.4 interlock sequence exactly like the central nervous system of the human body.
How so?
Well, if you accidentally place your hand on a red-hot stove, your body doesn't just register pain. In the exact same millisecond, an involuntary reflex arc fires. Your nerves scream an alarm, your muscles violently contract to pull your hand away, your adrenaline spikes to regulate your heart, and your eyes dart to assess the damage. It is an instantaneous, highly synchronized, multi-system survival response.
That is exactly what the code requires of an industrial facility.
Right.
That physiological analogy is perfectly aligned with the mechanical reality. When a detection system activates, the facility executes an instantaneous survival reflex. Step 1. A localized alarm sounds immediately to evacuate personnel from the immediate blast zone.
Okay.
Step 2. A facility-wide alarm is transmitted to alert central management and automatically dispatch the municipal fire department.
Got it.
Step 3. All coating delivery and recirculation pumps are instantly de-energized, severing the supply line so you stop pumping fresh fuel into the fire.
Critical.
Step 4. The conveyors and drive rolls lock up, halting the movement of burning material across the factory. Step 5. The gravity bottom drains automatically actuate, evacuating the 500 gallons of liquid down to the underground salvage tank. And Step 6. All primary sources of heat, such as the high-temperature drying ovens, are instantly shut down.
Wow. 6 massive facility-altering events, all hardwired to execute simultaneously without a single shilling pressing a button or making a decision.
For layout engineers, this reinforces the reality that you aren't just designing a tank and routing a pipe, you are weaving a highly integrated mechanical, fluid, and electrical web.
It's all connected.
Yes. The fire alarm control panel must be in constant communication with the fluid pumps. The optical flame detectors must be hardwired to the gravity drain valves. If your fire alarm system isn't intricately linked to those bottom drains, the fire will simply outlast the finite supply of your suppression agent.
And there is a critical, counterintuitive caveat to this interlock web regarding the ventilation system we talked about earlier.
Yes, this is a frequent point of catastrophic confusion in system design.
Because usually you'd want to shut everything off, right?
Right, but with almost all suppression systems like overhead water sprinklers, water mist, or dry chemical powder, the mechanical ventilation systems must not be interlocked to shut down with the fire alarm.
So you leave the fans on.
The massive exhaust fans must remain fully operable. They must continue pulling deadly carbon monoxide, toxic combustion byproducts, and unburned flammable vapors out of the building. You desperately want that exhaust fan running to maintain visibility and breathable air for the responding firefighters.
But there's one exception where leaving the fans on would destroy the entire suppression effort, right?
Correct. The only exception is if your facility utilizes a specific type of suppression, such as a carbon dioxide total flooding system.
Okay, how does CO2 work?
CO2 systems extinguish fire by rapidly flooding the entire room with heavy gas, displacing the oxygen until the fire suffocates. This requires the room to be completely hermetically sealed.
Oh, I see.
If your interlock fails to shut down the exhaust fans during a CO2 dump, the massive fans will simply suck all of your life-saving, fire-suppressing gas out of the room and vent it into the atmosphere. The oxygen returns, and the fire burns unimpeded. It is a delicate, highly specific balancing act of atmospheric control.
All of this complex code, the 6-inch kinetic buffer, the 25% LFL limit, the cone calorimeter testing, the simultaneous interlock discharge. It can feel incredibly abstract when you are just staring at blueprints.
It can, yeah.
But safety regulations are quite literally written in blood and ash. To truly understand the gravity of these codes, we have to look at what happens when the physics are ignored. We are pulling this directly from Annex B of the standard, which serves as a historical ledger of industrial disasters.
Annex B is sobering material. It meticulously catalogs the historical fire record for these specific operations.
Where do they usually start?
It begins by identifying the most common ignition sources. And historically, these multi-million-dollar fires do not originate from some complex, highly unpredictable chemical anomaly. They originate from basic, preventable failures in the code we just discussed.
Like what?
Static electricity violently discharging during a routine solvent transfer because an operator forgot to attach a simple grounding wire.
Yeah.
Workers illegally smoking directly inside the vapor boundary layer. Open flames from unpermitted hot work, like a maintenance crew welding near a Division 1 zone. Or a simple electrical arc caused by an engineer installing a standard, non-explosion-proof light fixture in a highly classified area.
The annex actually draws a sharp, terrifying distinction between a typical fire and an out-of-control fire.
Right.
A typical fire is one where the facility adhered to NFPA 34. A spark happens, the surface of the tank ignites.
Yeah.
But because of the layout, the fire is confined to the tank and the slope drain board. The simultaneous discharge system activates, the tank drains to the salvage bunker, and the fire is completely extinguished in under 3 minutes. The factory cleans up and everyone goes home safely.
That's the goal.
But the out-of-control fires, those are the ones that result in multi-month production shutdowns, massive structural collapse, and millions in property damage.
And when investigators trace the root causes of those out-of-control fires, they almost uniformly point to system failures. But I don't mean mechanical failures like a gear snapping. I mean failures of maintenance and human oversight.
Give me an example.
Suppression systems failing to activate because the thermal detection relays were coated in years of baked-on polymer resin and physically couldn't sense the heat. Systems failing because layout engineers only aimed the nozzles at the liquid tank, entirely ignoring the wetted drain boards directly adjacent to it, allowing the fire to easily outflank the sprinklers.
I was reading through Annex B, and one layout failure that blew my mind involved the manual pull stations.
Oh, yes, the pull stations.
Engineers placed the emergency pull stations entirely too close to the dipping tank. A fire starts. The thermal radiation spikes instantly to over 1,000 degrees, and the wall of heat is so intense that a worker physically cannot reach through it to pull the alarm handle.
It's tragic.
It proves that layout engineers have to anticipate human panic and raw physics. If you mount the emergency brake inside the burning engine compartment, it is completely useless.
Absolutely.
Another historical failure point that fascinated me is what the annex refers to as splash spread. We've trained generations of people that if they see a fire, they should immediately grab a red fire extinguisher and spray it.
Right, that's instinct.
But historically, fires have spread catastrophically in these facilities because well-meaning, panicked workers grabbed a portable high-pressure fire extinguisher, ran straight up to the burning dip tank, and discharged it directly downward onto the surface of the liquid from close range.
It creates a violent splashing effect. The pressurized gas from a CO2 or dry chemical extinguisher exits the nozzle at over 100 psi. Blasting that into a liquid surface acts exactly like smashing a spoon into a bowl of soup, except the soup is boiling, burning solvent. The high-pressure blast physically excavates the liquid, splashing burning coating material out of the tank, across the factory floor, onto the workers' boots. And crucially, it exposes the structural steel supports of the tank to direct flame impingement.
That's horrifying.
The worker, acting on basic training, inadvertently takes a contained 50-square-foot tank fire and aggressively spreads it across 400 square feet of floor space.
Speaking of collateral damage, I couldn't believe the details of the computer room incident listed in the annex.
Oh, that one is a classic layout error.
The fire didn't even breach the walls of the server room, yet it completely destroyed the company's infrastructure.
The computer room disaster is the ultimate case study in macro-level facility layout. Annex B details an incident where a facility planner decided to locate a highly flammable process tank entirely too close to the facility's main computer server room, failing to install adequate fire cutoffs or the mandatory 2-hour fire-rated separation walls between them. A fire broke out at the process tank. The suppression systems activated, and the fire department arrived. The fire was eventually controlled and extinguished before the flames ever touched the server racks.
So they saved it.
Well, no. Because of the proximity and the lack of structural isolation, the intense heat, the highly corrosive thick black smoke, and thousands of gallons of suppression water completely permeated the computer room. They managed to save the building's outer shell, but they entirely destroyed the IT infrastructure, the data, and the operational capacity of the business.
It perfectly loops back to the very first point we made today regarding location. An engineer can design a mathematically flawless, interlocked, beautifully drained, intrinsically safe dip tank. But if you place it next to the server room without a heavy concrete firewall, you haven't actually protected the business.
Exactly. Engineering can only take you so far. Spatial layout must anticipate the collateral damage of smoke, heat, and water.
So what does this all mean for you? The layout engineer, the facility planner, the curious mind mapping out the mechanics of disaster prevention. Let's summarize the blueprint we have extracted from this deep dive.
Good idea.
First, location is the foundation of survival. Keep these high-hazard processes out of the basement. If you absolutely must go subterranean, prepare for a monumental engineering challenge regarding egress paths and active vapor capture.
Second, respect the fluid dynamics. Maintain the 6-inch kinetic buffer so your high-pressure sprinklers don't cause a wave of fire, and ensure your massive fluid tanks can gravity drain their fiery contents to a safe, underground salvage bunker in under 5 minutes to break the war of attrition.
Third, control the invisible physics. Respect the 25% LFL limit to account for heavy vapor slugs. Understand that your exhaust fans are the respiratory system of your facility, and if they stop breathing, your entire electrical process must instantly die via hardwired interlocks.
And fourth, automate the survival reflex. When the worst happens, your system must execute a simultaneous multi-front assault on the fire while instantly severing the fuel supply, the heat sources, and the mechanical conveyors.
It truly is a symphony of passive architecture and active mechanical intervention. When a facility is designed correctly, strictly adhering to the mechanics laid out in NFPA 34, it stands as a marvel of modern industrial safety engineering.
It really does.
But I want to leave you with one final, slightly provocative thought to mull over as you look at your blueprints. We have spent this entire deep dive analyzing the physics of vapor boundaries, millijoule limits of intrinsically safe wiring, and the thermal resistance of 2-hour firewalls. But if you flip past the engineering tables to the very end of the code chapters 10 and 12, which govern operations, maintenance, and training, you confront the ultimate vulnerability of any design.
The human element.
Exactly. As an engineer, you can design the most brilliant, mathematically perfect, fully automated, interlocked dipping facility in human history. But if a tired worker on the third shift leaves a pile of solvent-soaked cleaning rags sitting in the corner of the room, rags which undergo exothermic oxidation and can spontaneously combust in the middle of the night,
All right.
or if facility management neglects to train the floor staff on how to properly sweep a fire extinguisher from a safe distance instead of blasting the liquid surface, your brilliant, multi-million-dollar engineering marvel will still burn to the ground.
An incredibly sobering and vital reminder, the most sophisticated engineering must always account for and actively manage the human element.
The ultimate safety feature in any manufacturing facility isn't a pipe, a gravity drain, or an optical sensor. It is the culture and the training of the human beings operating the machine. Thank you for joining us on this deep dive into the mechanics of industrial fire protection. Stay curious, design safely, and we will see you next time.